We're dealing with concentration today, and what we're looking at is just kind of what is concentration, and it's going to relate directly to what we talk about with solutions as well. So concentration is basically how much of your solute is dissolved in a solution. There's different ways that you can measure it, but we're going to look at a couple different ways today. When you're talking about a solution, and again, we'll get more into that later, but when we're talking about a solution just means that you have a solute dissolved in a solvent. So a solute is whatever is in the smaller quantity. So what are you mixing in? So when we typically think of solutions, we typically think of aqueous solutions, which means they're dissolved in water. And so the solute is what you're adding in. So like the Kool-Aid, the Crystal Light, the lemonade, that kind of stuff, the coffee, that kind of stuff. The solvent is the thing that's in the larger quantity, and typically for us that's water. It does not have to be an aqueous solution, and there's lots of instances where they're not aqueous solutions. So metal alloys are an example of technically their solution, their homogeneous mixture that has a solute and a solvent. It's just not in water. But a lot of the stuff we look at will be aqueous, so that's why we talk about in context to that. And then just really generally, you've all heard this before, you can have dilute concentrations or you can have concentrated solutions. And dilute just means you don't have very much dissolved, and concentrated just means that you have a large amount of the solute dissolved. There's a couple different ways you can measure it in science. One of the ways you can do is parts per million. You can even do what's down here, the ppb's, parts per billion. And these are obviously for very small amounts of things. These are usually for drinking water additives, pollutants, things that we don't have a lot of. These are also typically for things that are pretty dangerous for us, because if we're measuring them out to parts per million, parts per billion, there's probably a reason for it. So just for example, if you have city water, any drinking water additives would be measured that way. Some different atmospheric pollutants, stuff like that. But if you see ppm's or ppb's, it's just a way of measuring a concentration, and obviously, hopefully, a low concentration on most of them. Percent composition is another one, and we'll actually look at how we do percent composition. This is one they typically use a lot of in biology for solutions, because you're not really ready for, you haven't done moles yet. We don't like it because you can't compare one solution to another. So you can't compare a solution of salt water to a solution of acid. You don't have that ability. So that's why we don't use percent composition, but you can use it. Oops, sorry about that. The one down here, though, that we typically use is molarity. And what we have is basically it's how many moles of your solute divided by your liters of your solution. And this is just a really useful thing because a lot of times they don't give you your volume in liters. They give it in something else. So all of these equal each other. So 1,000 milliliters, 1,000 cc's, 1,000 centimeters cubed, a decimeter cubed, all of those equal a liter. And again, you just want to make sure that that is what it really is for it. He's kind of cut off down here, but this is a bad chemistry joke, saying that it's a 1 molar solution because we have 1 mole in a liter of solution. So again, bad chemistry joke. When you were talking about molarity, it's capital M, and not Michigan, because I'm not from Michigan, but anyways. So it's the big M for molarity, and it's very important when you are making solutions. And over here there's a picture. It's a really bad picture. You should never make a solution this way. But a lot of times in lab you're going to make solutions, and this is a way that if I say, hey, you need to make this solution, you can do this. So here's an example of one. If I ask you to prepare 500 milliliters of a 1 molar solution of salt water, how would you do that? And the first thing you have to do is we're talking about molarity, so you need to use your molarity equation. And what I did here is I took my molarity and I plugged it in, and I don't know how many moles I need, and I divided it by my volume that they want me to prepare in liters. So I did a little conversion here first. That's just a metric conversion. If you have questions on that, you can always see me. So what I do is I get my moles of sodium chloride, and then once you're here, this is just a mole conversion, so what we've been doing before. So we took our 0.500 moles of sodium chloride. I looked up the molar mass of sodium chloride, 58.5 grams, and again, my moles cancel. And over here, it tells me exactly how many grams of this I would have. So if I was going to go make this solution, what you would do is you get maybe 200, 250 mils of water. I'd measure out exactly 29.3 grams of salt. I'd dissolve the salt in the water, and then I would add water until I reach that 500 milliliters. You don't want to have the 500 milliliters and then just add the salt, because the salt does take up a little bit of room, a little bit of space. So what you typically do is you get like, you know, maybe 50-60% of the liquid, you make your dissolving, and then you just go up to that 500 mils. But you would have this much salt dissolved in about 500 mils of water. Next one is if I say, hey, I made this solution, but I don't know the molarity, you can do that as well. And again, you know that you're dealing with molarity because they're going to tell you. So in this case, I'm going to use this equation, and I need moles and I need liters. So the first thing I did here is I got my moles. So I said I must have been on a salt kick that day. And if I have 37 grams of sodium chloride, how many moles is that? So this is just a mole conversion. 1 mole of NaCl is 58.5 grams, and I get my moles. And you'll notice this is to correct sig figs. And then the only other thing I need is I need my liters. And you can see here what I did is I just took my 150 mils, divided it by the 1,000 to do my metric conversion, and plugged it in here. So I have my moles of my salt divided by my liters of my whole solution, and I get either 4.2 big M or 4.2 moles per liter. And either of those are acceptable. They mean the exact same thing. It's just really a personal preference on that one. And then you can also go this way where they're asking you just something about your molarity. So we want to know how many moles, which is right here on our equation, are present if we have a certain volume of a certain concentration HCl solution. So you can see here have our molarity, we have our milliliters, and again you can easily turn that into liters, and all I'm doing here is just multiplying that up so it gets canceled out, and I can figure out that I would have to have 0.326 moles of hydrochloric acid. Now that's not the most useful place to stop. I mean, we certainly can, because in this situation that's what they asked us for, so we would stop. But what we do typically in chemistry is we go to grams so that we know how much of something we need to make from it. But in this case they just wanted us to go to moles and stop. And last one is going just another one with molarity. So we want to know how many grams of salt are there in 2.5 liters of a 1.5 molar solution. So again, I'm using molarity, and anytime they say the big M or they have like a certain molar solution, that means molarity. So I know my molarity is 1.5 molar. I know my liters are 2.5 liters, and I'm solving for X. So I got 3.75 moles. Rounding it up, I get 3.8 moles of sodium chloride. If you don't round until the end, that's okay. I won't, like, it's either ones or I'll accept for this one. Technically, you should really round to 3.8 and go from there. But so we have our moles, and then again, once we know our moles of our chemical, we just do our mole conversion to get 2 grams. And again, make sure that you go down to 2 sig figs. So it should just say 220 grams of NaCl. There should not be that dot there because it should only be 2 sig figs. So ignore that. It's just 220 grams of NaCl. So that is molarity. Those are the general things that you're going to do with molarity. And you'll notice it's going to be pretty easy to tell molarity because it's going to have molarity in it, or they're going to ask you for molarity. And typically that involves like a mole conversion and then using the equation.